We are going to look at blind signatures and electronic cash today. This is the last chapter this is the last section in chapter 4. First of all, what is blind signature? Well, blind signatures are a technique that allows someone to sign something without seeing it. What that means here is that, let's say I have a document M, and I want a signer to sign M. That means putting his signature on it, but I don't want the signer to see what M is. So this is a blind signature. Blind signature has an important application in electronic cash. So blind signature can be realized using RSA. So here is how we use RSA to generate a blind signature. So here you can see I have a message M, and that's the message M I want the signer to sign. And the signer has a set of RSA keys. Of course, N is one of them, E and D. So E is public key, and D is the private key, and the signer uses D to sign this message M. So this is what I want. I want the signer to provide M to the D's power, mod N to me, because that is his signature on M. But I don't want the signer to see M. So the idea then is I am going to hide M inside another message, M sub R in this case, by using a blind factor R. So that blind factor R, which is less than N, is an integer such that R and N are relatively prime. Okay, so because R and N are relatively prime, the inverse of R, mod N, exists. So I'm going to use R to hide this M inside another message. Okay, so if you look at here, I am encrypting R using RSA. Okay, so this part is encryption of R. And what I'm really doing is to obtain the multiplication of M and R to the E's power mod N. Okay, so that's MR. So I present this MR to the signer. The signer the signer won't be able to see what M is. So I present MR to the signer. Signer signs the MR, which means that signer will carry out this calculation. So this is raise MR to the D's power and take the modular. And the signature on MR is S sub R. Now remember, we can use fast exponentiation algorithm to compute this efficiently. So then the blind factor R is included in this signature. So we need to remove it from the signature. So this is done as follows. So we multiply M inverse mod N with SR. So that is equivalent to removing R blind factor R from this signature F sub R to get S sub M, which is this. So that's exactly what I need. Here is a quick proof how it works. I'm going to write this proof down in a separate video after this. Okay. So now let's continue on this topic. So let's look at how we use blind signatures in electronic cash. So first of all, to come up with a protocol for electronic cash, we first look at what properties we would really like to achieve. So first look at in general, what key properties real cash should have. So I have 4 bullets here. One is anonymousness. The other one is changing hands. The third is that cash of certain values can be divided into smaller values. And of course, it has to be very difficult to counterfeit using all sorts of technology, such as hidden images, sequence numbers, special kinds of inks, and high quality paper, that sort of counterfeit technology on cash. So the question then is, can these properties be duplicated with some sort of electronic cash protocol? So before we talk about actual implementation, so let's see what an ideal electronic cash protocol should have. And what we really like a electronic cash protocol to have is the following. Number one, anonymous and untraceable, or anonymousness and untraceability, which means that you don't know who owns that particular cash bill, right? You don't know who owns that $100 bill. Of course, when you change hands, you cannot trace it's a prior owner, that kind of thing. And it should be convenient. We know that electronic cash are used to pay for something, but you can also give electronic cash to somebody without really offering any products or services in return. And it has to be non-replicable, meaning that you cannot, only one copy can be used, right? So this is electronic cash, so it's easy to make a copy of it, but only one copy can be used. And it's transferable, because it's easy to understand. You can give this copy to somebody else, and that person can use it as its cash. And the last one is dividable. It can be divided into smaller values. So these are ideal properties of an electronic cash protocol that we really like it to have. Unfortunately, at this time, we don't have any protocol that can provide all of these properties. So what we are going to look at is a protocol named eCash. This protocol was devised in 1980s, in the 1980s, which satisfies many of the most important properties that we outlined earlier. In particular, it uses blind signatures to ensure anonymousness and untraceability. So here is how it works. Let B, capital B, denote a financial institution. For example, denote a bank. And let B's RSA keys be N, D, and E. Again, N is a product of two prime numbers, and E is a private key, such that E is relatively prime to phi of N, and D is the inverse of E, modular phi of N, meaning D times E is congruent to 1, modular phi of N. Okay, so now suppose Alice wants to buy an eCash dollar. So what Alice would do is the following. First, she generates a sequence number M at random. So this could be a random number she generates or follows on certain protocols she only to herself. So she generates a sequence number M, and that number is going to represent the eCash dollars she's going to buy. Then she uses a blind factor R to blind M. Okay, so this R is a random number. And what she does is to compute M times R to the east power mod N. Let's call it X. So in effect, this sequence number, small m, was included in this X, okay? But of course, anybody who sees X won't be able to know what M is without knowing what R is. Okay, now E and N, of course, are public. So Alice then sends X and her account number in the bank to the bank B. So B verifies that Alice does indeed have an account with B, and B will charges $1 from Alice's bank account plus some processing fee, and then signs X, okay, and send it to Alice. So then this X, which is a signature, we call it Y, is what Alice has. But then Alice needs to remove this R from Z. Okay, so what she does is to multiply inverse of R with Y. So this is equivalent to removing R. What she gets is M to the D's power mod N. So this is there's a sequence number now has bank's endorsement because the bank B signs it. So that means finally, Alice gets her eCash dollar, M comma Z. Z is M to the D modular N. So then, of course, Alice can use this E dollar to buy things or simply give to someone or whatever, right? So let's say B gets this eCash from Alice, okay? And so what Bob, let's say Bob has this eCash. Once this M comma Z is in Bob's hand, of course, nobody else would know. This comes from Alice because there's in no way there's any things left on this M and Z, okay? And obviously the bank doesn't know what, who creates this M either, because when the bank signs it, the bank doesn't see M. What he sees is X, okay? So he doesn't see M. So nobody knows who created M, and nobody knows the prior owner of M. Okay, so now Bob is the current owner. Let's say Bob wants to redeem this eCash dollar. So what he does is to send this M, Z to the bank and saying, hey, I want to cash this eCash dollar. And the bank verifies this M that's indeed endorsed by the bank by checking its signature. And then he gets, and then he needs to check to see whether this M has been cashed before. Okay, so if it has not been cashed, then the bank will consider this eCash dollar valid and record M in its database, indicating that this has been cashed. And then, of course, credit Bob's account by $1. So as you can see here, blind signature is used to make sure anonymousness of eCash dollar and untraceability. So there's a problem here. Well, actually, we can think of several problems, but we can at least think of two in this particular case. The first problem is that since it is easy to duplicate this eCash dollar M, Z, okay, let's say Bob has it and Alice also makes a copy and sends it to Charlie, for instance. And then, of course, let's say Bob is a legitimate person, but Charlie isn't. So the question then is, how can Bob stop Charlie from redeeming that cash, $E cash, before he does? Okay, so that is the first question that I would like you to think about. The second question is, how can we divide a eCash dollar into smaller values? Okay, so that's another question. But nevertheless, using blind signatures in electronic cash ensures unanimousness and untraceability, which is one of the most important properties that cash should have. Okay, that's it for today for this topic. We're going to move on to the next topic. And also, I'm going to write down the proof how to remove a blind factor with RSA in blind signatures in a separate video. Stop sharing and meeting.